Thank you very much for the invitation. I'm glad to be here, and I'm waiting for your questions. So I don't think I have to tell you, but please interrupt. This is not part of a course of 25 hours that I cut into 6 hours. So it's really open to what you are mostly interested into. So please direct me if there are things that you like more or less. So it's going to be about fluids and navigation. So fluids for life are kind of interesting because they are everywhere. So life happens in fluids. There are fluids within cells and outside cells, within organisms, outside organisms. Everything essentially happens through fluids, is mediated by fluids. So that's good for a fluid mechanician turned into a biophysicist, because that's a lot of interesting questions. And so one thing that I really want to convey in these lectures is that fluids are very different at different scales. And so that's why I'm going to try and talk to you about navigation. We'll say a few words about navigation in a second, in very different systems. And I'm not sure that I'm going to get through all of the systems that I'd like to show you. I love all of them, so it will be painful not to talk about it, but it's fine. So I'm not sure I'm going to talk about everything, but let's go through them, at least in this first slide, so at least I get to tell you something about them. Okay, what is this? Is it too small? It's more, oh, E. coli. What else? Who says sperm? Who says E. coli? It's E. coli. So that is great. Okay, so bacteria, this is the theme for today. So I'm not going to tell you much about this. We've heard from Lisa about run and tumble, and so we're going to say things about run and tumble in a slightly different way. So I won't spend much more time on this because we'll talk about it. Who knows what's this? What's the scale, actually? Guess. Sorry? Bacterial colony. What's the scale? 10 centimeters. What's the scale here? Microns. Okay. So that's exactly right. It's called the biofilm. So it's a bacterial colony that does interesting things. So from single bacteria, I would like to pass to colonies to talk to you about collective behaviors that we also heard about today, but we're going to talk about it in a slightly different way. So we are intersecting with what Lisa is talking about very nicely. And this is actually a movie. That's always nice to show. Okay, this, it's obvious what it is, I think. What is it? It's mouse. So we are kind of moving up in scale, and the mouse is doing olfactory searches. So it's sniffing the air, and it's moving to find the source of the odor that we are giving him. So we're going to talk about that. This is a very new entry, so I have very little to tell you about this, but it's great because it puts together this guy, so collective behavior, and this guy. So it's an individual that does searches, does navigation, but in it there are, the different arms are independent. So it's a kind of collaborative, collective behavior that occurs in a single organism. And it's a pretty cool movie that our collaborators took. Okay, what is this? What? Spores. How do you know? I mean, I thought that this was the hard one. Who knew it? Okay, well, okay. No, it was not Nicola. Did you tell him? Okay, great. So this is a very famous work. No, it's not very famous. Nobody knows about it, but it's pretty cool. It's about fungal spores. that are dispersed in the atmosphere, and guess what? They move, so there's some kind of navigation problem, and there are fluids because they're particles and they move in the air, and so it falls in the same category, which is pretty broad, lucky for me, which is living in fluids and navigation. So this is the very vague plan that I don't necessarily need to go through these lectures, but first of all, let me tell you something about what I mean by navigation. And maybe I'm going to ask you, what do you think that navigation requires? Let's define navigation, moving from A to B. What do you think it requires?
Space.
Space, sure. What else? Some energy, sure. Information, yes. Okay, so let's yes, a medium. Let's be a little bit more precise with the question. Let's say that you want to go to dinner and you're really hungry. What do you usually follow?
Yelp.
Yelp. That's a good one. So, for example, we normally need, in order to move from a point to another, we need our senses. Okay, if we close our eyes, our ears, and we don't smell, and it's hard, okay, to go from A to B. So we usually need senses. That's not the only thing that we need, and I'm gonna show this to you in the next slide, which hopefully nobody has seen this, or somebody has. Raise your hands if you've seen it. You are not allowed to talk? Anybody else? Okay, great. Okay, so we not only need senses, so just to introduce you to this really great experiment that is pretty old. At this point in time, in the early 19th century, most people thought that navigation was a series of instructions. So that's called a stimulus response. That means you arrive here, you turn left. Then you get to the traffic light and you turn right, and then you keep straight, and then you follow instructions. Okay, this is one way of moving from A to B. Of course, if you miss the turn, you're kind of screwed, but if you have other ways, if you have, for example, maps, then that gets you around. So this is what this experiment was about. So the first, I think, 4 or 5 days, rats were put in this maze, which was pretty boring, circular. They were actually put here, they would get here, and then they only had one arm to explore. Okay, there was only one possibility, and so they would go do all of these turns and get to the food. This was for a few days, and then they were exposed to this other maze. Okay, and of course the poor rats arrived at time 0 here, they got here, and then they went straight up to verify whether there was food, and there was no food. So what did the rats do? You're not allowed to talk. Pink shirt.
Explore.
Explore. Which arm? 1, 18, 15, 17, which one?
Was there actually food in the experiment or not?
In the experiment there was no food.
Okay.
It doesn't really matter for the poor rats, but it's interesting to see what he did.
No idea.
10? 10 or 9. These are the neighbors of the one that was the sure shot. Okay, what else? That's the wrong answer. We have a 6. We have a 1.
The maze going back to the start.
Going back to the start. Any motivation? Random?
Not because the
5. Somebody? What?
Look at the picture.
So I'm guessing because it doesn't, it might not have a sense of like maybe direction. It cannot maybe detect direction. So we go back to the maze because it looks like the.
He gets confused and goes back.
Maybe.
Because he doesn't know where he is. Definitely wrong, but interesting. Anybody has an idea why they answered any number? there were some, yes?
So I would see, I don't know if that's the case. I mean, you go straight and then you go left. So I'm thinking they went to the wrong thing. They said, okay, maybe they made a mistake. Then they go back and then they go left, and that's one.
So they memorized this turn and they were like, I have to go their way.
Yes.
Okay, that's almost right. Almost.
I was thinking 5 or 6 because if you do a projection from where you are there to the food correctly, that would be.
Who agrees?
What did he say?
If you
That-
do a projection to the food.
So then you go right?
5 or 6, that's
5 or
what
6.
he said.
I see.
Any other ideas? Somebody agrees with the argument?
But, I mean, with that argument, you're kind of assuming that the rat has a place map, which is
Yeah.
diagonal. But if the place map of the rat is just like left, right, up, down, like 90 degrees, then it really does go to 1 or 18. Yeah. I don't, okay, I'm
Ye-
definitely winging it, but this is.
Yeah, but that's the point. So, okay. So, any other hypotheses, ideas to test? Okay. So, he had the right idea. They almost, a large fraction of them goes to 6. And the reason is 6 is a shortcut. Okay, so they are able to compute in their heads shortcuts. So navigation is not only about instructions, it's not only about sensation, it's also about having in your head the possibility to play the future and to project outcomes, expectations about outcomes.
And
Okay.
outsmart Google Maps.
Outsmart Google Maps. That's pretty hard these days. But okay, one more point. What made the rat think that 6 was good? 6 was a shortcut to food. And food, why did he assume that food was there? Because of
The training.
the training, so his previous experience. So there is a very profound distinction between things that are goal-directed and habitual, okay? So our experience shapes our biases, our assumptions about the world, okay? We have a repeated experience of some kind, and we assume that this is gonna help us in predicting the future. Okay, and this is something that is at work here. Of course, the rat is having to play in his head future outcomes of different trajectories because he's choosing the shortcut, but also his future is shaped by his experience. Okay, so this is the last ingredient that you need for navigation. You need sensation. You need, sometimes you have instructions, and sometimes you have a map of space that is able to get you around even if you don't have an instruction right there. Okay, so of these 3 things, I'm mostly going to talk about sensation, but the rest is going to be in there somewhere, and so I just wanted to mention them. Yes?
I was wondering, did they try out like a case where they have the original class and the class 6?
They had what?
That they only have like 2 classes, the original one with the edges and then the class 6?
Okay, so maybe a little bit of history. This is the first experiment, and since the 50s, they've done everything you can imagine on this kind of thing. So I'm not, I don't have it in my mind. I don't remember it, but I'm sure that's been done. It's been done with sensation, without, with vision, with odor, with no odor, no sensation, no. And they're pretty much able, so somebody said, you said that they might get confused and not knowing where they are. In order to get them confused, you really need to work hard because their map of space is anchored in any kind of sensation. So if there's any small light, and even themselves, they leave traces of odor on the ground and they're able to use that to know where they are. So it's really hard to get them confused. Yes?
Based on this, I'd say that probably 5 or 7 should have been secondized. Why is 1 secondized?
That is a good point. You know, I have no idea. I think, so these were not so the number was 56. I read it today. 56 mice, which is rats, which is unusual for today's experiments. You tend to try and save on animals for good reasons. So I'm not sure if this is a statistical fluctuation or not. 8 seems large for a statistical fluctuation. It's a good point. I don't know.
I mean, it correlates.
It's like those are straight line paths, right? So
Yeah.
it's probably just using a L1 sort of distance,
Right.
like moving straight lines or something.
So he thought that he could go this way and this way, a little bit what Eleni said, that you would go 18, but 18 is not, oh, it's not here.
I mean, I need to say.
Oh, sorry, maybe this is, I think this is for the one that's done like this, that doesn't have this. Sorry, but the point is, I mean, this peak shows up all the time. And then the rest, I think because it gets only to 12, I think it was one where you only got to 12, and these were not there. They were not there. It was a different experiment that they were not there. Sorry, but that was a good point. Yes?
I have a question. So if one records like neural activity for the mouse that is going in the maze, like there are some neurons that spikes at particular location, like some
Yes.
special neurons. And if like mouse is taking the shortcut, does it use those neurons or not?
Probably not those, because those are thought, actually they're very interesting neurons, because when they were discovered it was thought that it was like a Lagrangian measure of space, like there is something interesting happening here and I have a neuron dedicated for that location. Really, it seems like it might just be a memory neuron that is anchored to space, so it's not totally clear, but I don't think they would be the ones that are used, because the environment is different, so usually the map changes.
Yeah, but let's say like we are thinking about making a shortcut, right? So we are kind of like trying to remember all paths and figure out like how to make a shortcut. So we have to use that memory, right?
Yes, but I wouldn't think that it's the place cells that are used. I think they would be the grid cells, because the grid cells are those that tell you where you are in space, with no particular reference to an event or something that is of notice. You know where you are with respect to the edges of your environment, and those are grid cells. They are in a different location in the brain, and I think those are the ones that allow you to make computations about trajectories. But yeah, they were discovered, there were Nobel Prizes, so this is a very exciting field to be in. Okay, and just as you all know, biases are there for all organisms, higher organisms. This is a bias that I like to show. It's from this paper, and it says observers with different preconceptions interpret the same piece of evidence in ways that conform to their initial views. So again, animals have biases, and it's not like they are isolated from the environment. They have sensation that connects them to what the world is doing, but they also have biases. So their behavior is determined, in this case, who you vote. Okay, maybe I should tell you what this is. What this is they ask people whether the choices George Bush did in a matter related to economics was good or bad. And what this shows is that strong Democrats would always think that the choices were bad, and strong Republicans would always think that they were good. But they, of course, and you see one striking thing is the difference between these two is constant. So it's not like you can really do anything. People will vote whatever they want to vote, no matter what you do, which is this is pretty bad. But there is a little bit of modulation, which probably comes from what he was actually doing. So from sensation, you are in a world and you are realizing that things are getting better or getting worse. So your opinions slightly change, but still you'll vote the same person. Okay. So this was just to say we're not going to talk about who you vote or whom I vote or anything that relates to politics, but it's just to introduce the idea that navigation is complicated, because it's complex, I should say. It's an interesting problem. It requires you to understand what the animal wants to do because of prior experiences, because of goals, and because of habits. Okay, and then this is the subject for today. What this is a very old essay which dates 1898, which shows that bacteria are able to navigate to locations of interest. In this case, there was an attractant given by this capillary tube, and it was observed that most bacteria would get there. And so we'll use this as a very good example of a navigation problem that is well understood, well formalized, where everything from the computational level to the algorithmic level and even to the implementation level is completely understood. And then we'll move into more unknown territory. Okay, before I get to some calculations about the basis for chemotaxis, everybody has heard the name, the word chemotaxis, right? Okay. Before doing that, so because bacteria will have to move from A to B, and bacteria are small, we've heard about this already a little bit, but they move in fluids, and fluids obey a very famous equation, which is the Navier-Stokes equation. Okay. Okay, for everybody has seen this in their lives? Okay. Inertia, okay, so accelerations, viscosity, pressure gradients, external forcing. Okay? And if you do an order of magnitude calculations of this nonlinear term, this is what makes this equation infamously complicated to understand, to solve numerically, analytically, and we'll talk a little bit more about this. This nonlinear term, its order of magnitude is u squared divided by length scale. Okay, and the order of magnitude of viscosity is kinematic viscosity times u divided by L squared. Okay, and so bacteria are very small, so L will be of the order of a few microns. If we do inertia divided by viscosity, this will be u squared divided by L divided nu u L squared, and this is then u L divided by nu. And this is the, sorry? Reynolds number, yes. Okay, our hero Reynolds number. Okay, so let's calculate it for a bacterium, just very quickly. U is about right or wrong? Right or wrong? Meters per second? No, okay. Microns per second. Nu, somebody knows viscosity of water? Yeah, you know it in the other system. I know it in SI. But that's the right number. It's because I remember the 100. Okay, U, nu, L. Okay, so UL is already ordered 10 to the minus 12, and there are two zeros here, 10 to the minus 10, and here there's 10 to the minus 5. So Reynolds is ordered 10 to the minus 5 for a bacterium. Okay, so very small. So forget about inertia. The equation becomes much more simple, incredibly like a different world, and this is why things are different at different scales. But the intuition that we have about how things work at low Reynolds numbers are not exactly easy. Yes?
So is this assumption of like letting Reynolds number go to 0?
Why assumption?
So my question is that a singular perturbation or a regular perturbation?
there is no perturbation. I'm not making any assumption. Reynolds is very small, and so this you can eliminate. The other thing that you might know is that when Reynolds is infinite, you cannot neglect this.
Right. So
That's the singular perturbation,
okay. So but not the other way.
but not the other way.
Okay. So that's what I was asking.
Okay. Okay, so why I was saying that things are not very intuitive physically at low Reynolds number, it's because there is no acceleration. So things move as long as you push them, and then the moment you stop pushing them, they are not going to move anymore, including fluids. So a fluid contained in a container will move as long as the edges, typically, the borders of the container move, and then it will stop instantaneously. Okay, so this makes it for a fluid dynamics that's reversible. Okay, so these are very famous movies that maybe Lisa wanted to show, but maybe not, hopefully not, because no, great, okay. Somebody has seen them? Okay, so these are movies made by G.I. Taylor, who was a famous fluid mechanician, to show this concept that things are reversible at this low Reynolds number. So if you do this here, this is a cylinder, and he's going to move the cylinder, and he's going to mark some fluid particles with a die. And he's going to start turning pretty slowly, okay, to remain at low Reynolds number. It's done in a fluid that's very viscous, so the Reynolds number is really very small, even if the scale is large. And what he did, so he turned in this direction, and now he's turning in the other direction, coming back. He's not putting a lot of effort into controlling exactly how he's moving things, but just coming back. Just coming back, applying the same number of turns that he originally did on the way to come. And guess what? There's no smearing out of the scalar. It comes back exactly where it is. That means that those fluid particles that were marked initially will go back exactly to the same initial position. Okay, and this is, do you find this intuitive? When you steer...
Okay, so I have a dumb question.
Yes.
If I put a dollop of something like dye or yogurt into honey, it will not do that.
Well, that means it's not low Reynolds number.
But isn't honey the like...
Honey should be good. So if you have you ever done it? It should, because this is molasses, I think. It's done with the... have you done it? You're asking because you did it? You're not answering now. That's confusing. Did you do it or not?
You need like a pot of honey, right? You need a pot of honey.
You can do it in small. You can. This is pretty robust, and the reason why it's robust is because the reason why this goes back is because it's reversible. So that means if you do it, if your movement with your hand is faster or slower, it doesn't really matter. The only thing that matters is that you redo exactly the same perturbation that you did on the way to come. When
So hard in the...
hard? No, because it's just you count the number of turns. That's the only thing you have to do. You don't really have to control how fast you did it or slow. Try it.
Honey and water or honey?
I was thinking honey and yogurt, but it's true you do it in the reverse ratio. You need a pot of honey and put in a drop of yogurt, right?
Yeah, but you're not going to see it.
See-through honey.
Honey, yes.
I vegan honey.
Vegan honey, yeah. I'm sure that would work.
Stirring with a spoon or something? What do you do?
No, with that might be the reason. So if you stir with a spoon, it's different because you're not controlling the perturbation. What he's doing here...
Saying when you said that the reverse perturbation, it's hard because of the stirring.
Oh yeah, it won't work with a spoon. What he's doing here is he's shearing the borders, and so that's easy to control, to go back.
It would
Exactly.
work with a blender, though. If
No,
you
I
can
don't
reverse-
think it'll work with a blender.
No.
reverse
Then you
polarity.
put in and I don't think it'll work with a blender.
I mean, if you can turn it very, very slowly, like, yes, it will. Okay, so next movie is about the consequence of this very basic, yes. Sorry, I didn't hear.
Large dissipation is usually associated with building
That is a good question. It's not like dissipation will be small in the other regime. It will just be pushed to small scales. That's one thing that might just answer it, and it might just be the answer, actually. So it's not like small Reynolds means large dissipation. In fact, at large Reynolds, you have, that's what I was trying to say, it will be the topic for tomorrow. This, although this ratio becomes very small, the dissipation coming from this remains constant. It's a finite number, and that's because gradients get pushed to smaller and smaller scales. Okay, so this is a statement only about forces, and then dissipation is a different story.
I think it's because in that limit equation becomes time reversal in the area.
It does, but his question is why, because normally this is not the case. Yeah, formally, yes. There's no time anymore, so it cannot be different than that. But his question is why, well, actually, that is also an answer, which is, so right now I'm talking about steady states. Okay, so I'm not considering this term, which is, would make this become a pure diffusion equation, which is not reversible.
I mean, like if you track heat, for example, if you track...
Yeah, that's right. That's right. If you have this term, then you don't have reversibility. That's right.
There's another equation for heat, and so like if you really
Yeah,
waited long enough time, then you would not be able to reverse it.
no, of course. Diffusion is not at all reversible, and that just implies that you have to keep this term, which is not what I'm doing here because it's just in a steady state. If you do it slowly enough, you're good. Okay, what's the implication of this? The implication of this is that if you are a bacterium and you want to move, you need at least a few degrees of freedom in the following sense. If you are an organism and you're trying to move, mechanically what you want to do is you want to deform the shape of your body in a cyclic way, in the sense that you want to do something and then be able to repeat it so that you keep going. Okay, so you have to do a cycle, but we just saw that if you during the cycle, on the way to go halfway, you do a series of perturbations, and you do the same series of perturbations when you move backwards to get to time zero, to your initial configuration, you're not going to go anywhere. Right? We just saw it. And so that implies that an organism that only has one hinge will never move. This is called the Scalp Theorem. So a scallop at low Reynolds number would never move. It only has one hinge. So there's no way it can get back through a different path of perturbations. And that's what this experiment is showing. This is exactly what I just told you. It's a hypothetical swimmer that only has one hinge, with only 1 degree of freedom. So it's trying to make a cycle, but to make a cycle, it has to go back and forth through the same series of states. And so if you put it in water, that's a high enough Reynolds number and it can move. But if you now switch to, what is it, I don't remember, it's probably honey or molasses, then it doesn't go anywhere. Okay, so this is also pretty unintuitive if you think about it. If you have something that does this, you would expect it to move because it does in water, but not at low Reynolds numbers. Okay. And so one thing that you do to get around this problem, if you are a bacterium, is you can have something that turns. And if you have something that turns, you might get back to the original location without ever having to go through the same configurations that you did before. And so that's what the smart guy did here. So this is the one that didn't work. And now he has 2 spirals, and the spirals get the swimmer to go. Okay?
Why the rotation works again? Because of the shape.
Why is not explained right now. That's absolutely not obvious, and also the direction of motion is not obvious, because you would imagine that things like your intuition is about how you swim, and that's high Reynolds number. At low Reynolds number, the reasons why this move is not the one that you might think. And I don't remember the argument, but it's it's something that you can prove.
Even for human swimming, you're doing non-reciprocal, you're doing non-reciprocal motion.
That's
If you try to
typically,
go like this, you will not go very efficient.
it's not efficient, but you will move,
No, of course.
which is not the case here. Here you go just nowhere. But that's the point.
How-
Yeah, but for us, the Reynolds number is never close to zero ever. So, okay, good. So run and tumbles, and then I'll move to the board. Okay, so this is what bacteria do typically to move through fluids. They have flagella, and this is E. coli, as we have said before. E. coli has several flagella, and they can move either counterclockwise or clockwise. And for some reason, when they move counterclockwise, they are in a bundle. Okay, so that produces runs. So these are three instances of trajectories. And you see here, for example, you have a run. And then randomly, in time, the flagella will start to move the other direction. And when that happens, the bundle sort of disassembles. And so the body of the bacterium reorients. And that's a tumble. So trajectories of bacteria are random walks that are constructed with the series of counterclockwise and clockwise rotations of the flagella that produce run and tumble. Okay. And so just to fix the things, when there are no attractants, the transition between these two states is random. There are transition rates that are constant. Typically runs are longer than tumbles. They are about 1 second. Tumbles are much shorter. The durations are Poisson, and you have a typical reorientation angle, which is this number. Okay? And now we are interested in understanding how the behavior of a single bacterium modifies when I add attractant. And when I add attractant, a very famous result by Berg is that if you add the attractant here, this is the fraction of bacteria that are running, and we'll talk about this function. You observe that the fraction of bacteria that are running increase. Okay? And then transient, so this is about 1 second, the extent of this increase in the fraction of bacteria that are running is about 1 second. And then transiently, you have a decrease with respect to the baseline. So it means that with respect to the equilibrium, more bacteria reorient. And then they get back to the original baseline. Okay? And so the question is whether this is interesting, whether this tells us something about what bacteria do. And we know this is the base to define chemotaxis. So in the next lecture, we'll see how this produces chemotaxis. Okay? And we'll try and see the computational principles that make this an efficient way of doing chemotaxis at this low Reynolds and Piclet numbers. Okay? Everybody has seen this before? No. Okay, so this is not, completely new for everybody, but for a considerable fraction of you. Yes. Okay, good. Okay, so what does this do to our bacteria? Okay. So we've said that we have two states for the flagella. One is the counterclockwise, which is the run state, and the other one is the clockwise, which is the tumble state. Okay, and we have rates. This we'll call it K run, the rate of transition, and this we'll call it K tumble. Okay, so the probability that the bacteria is gonna be running at the next time step, so PR of T plus delta T comes from two contributions. Either you were already running at time T, but in that case you don't want to transition. Okay, so it's 1 minus the transition rate from run to tumble. Okay? And then there is another contribution, which is the probability that you were tumbling at the previous time step, but you transition from tumbling to run. And so this is P of tumbling to run. Okay? And now because you're either tumbling or running, this is 1 minus PR. Okay? And what are the probabilities? So the probabilities are simply written like this. Is this too far into the corner? Can you see? You cannot see. So if I write here, it's better. Okay, this is just a two-state Poisson process. There's nothing really special right now. We don't have any chemoattractant yet. And this becomes an equation for the probability that you're running. And what do we have? Here we put this on the other side, and so we have a minus PR at time t times KR. And then there is a plus 1 minus PR of t and then KT. Until here it's fine, or? Okay. Okay, so this is the derivative. And so if we are at steady state, so the steady state of this distribution, it's just defined by the transition rates. So you get from here PR of t times minus KT minus KR, and you have equal minus KT. And so without chemoattractants, and sorry, I should eliminate the T because I'm at steady state. Okay. Okay, so this is just at equilibrium with no chemoattractant. And now what did Berg do? And what you can do is now you add a chemoattractant at T equals 0, and then you do the following experiment. You take a lot of cells, and you either, so you can do it different ways. The way Berg did it is, have you heard about impulse response and the tethering assay? So that was a very clever way to measure the rates of tumbling and running, which is with a chemical treatment, he shaved essentially bacteria. So a lot of them will remain with just one flagellum. A lot of them would die, and a lot of them would be useless. But he could get a lot of cells with just one flagellum, and so then he attached that flagellum to a surface, and then he observed the motion of the body. And that would be the inverse of what the flagellum was trying to do. And so by doing this, at time t equals 0, he would add a chemoattractant, and he would measure the fraction of cells that would keep running, keep tumbling, and measure the time courses. What do I mean is, for each cell, he would record, so this is cell number 1, this is cell number 2, this is cell number 3, and he would have for each cell its state. Okay, this would be run, and this would be tumble for cell 1, and then cell 2 would do a different thing, and et cetera, et cetera. And then just adding this up, he would have fractions. Okay? Fraction of cells tumbling and fraction of cells running. So if you say that run is 1 and tumbling is 0, just by adding this up and dividing by n, this is the fraction running. Okay, it doesn't matter if you don't read it. It's just the sum of the individual traces, and it's what he did to get this sum. It's called the bias, Okay, and you can also subtract the baseline to get a response that tells you how much the chemoattractant affects the original baseline. Okay? So now if you do that, it turns out that chemotaxis is a great system because it's linear. Okay? And I'll define what linear means, but just give me a second to remind you what a linear transducer does in general. Okay? A linear transducer will be this black box. Okay? L as in linear. It gets an input, F, and it spits an output, L of F. Okay? This operator is linear. That means that if you ask what's the response for a linear combination, you'll get the linear combination of the responses. Okay. Now, linear transducers are defined by the stimulus response to an impulse. Okay, the impulse response is everything you need to do in order to characterize a linear transducer. What is it? Okay, so take what is an impulse. The impulse is defined by the following algorithm. You take your favorite shape for a dome-shaped function, and you call it f0, and then you calculate it in t divided by tau, and you multiply by 1 over tau. For tau that tends to 0, this becomes a spike. Okay? And what's interesting is that as you go to tau that tends to 0, what you chose as your favorite function doesn't really matter. Okay? All you have to know is what's the response of your linear system to this impulse. Okay? And we'll call it k as in kernel. So L of h is k. Okay? Okay. Now, why is this interesting? This is interesting because now take a function, f, which is varying. It's not the simple impulse anymore. Okay? And it's a function of t. And now divide it in little chunks. Okay? We'll call this tau e. Okay? And this is delta tau. And this is the function calculated in tau I. Okay, so now you can expand your entire f, you can approximate it in chunks. So that means that you write it as a sum for I that goes from 0 to n of what? Of your impulse h, translated of tau I, I'm just calculating it in t minus tau I because I need to center it in the location where I'm expanding my function. And then I have to multiply by the surface of this rectangle, which is f of tau I times delta tau. Good? This, by the way, I have to normalize it to 1. The area of this is normalized to 1. Okay? And I'll call it C because otherwise it's confusing for here. Okay? Now we are ready to calculate what's the response to this function, because it's just a linear combination. The transducer, the operator that tells me what's the response of the linear transducer is linear, so everything passes in. Yes?
Sorry, I don't understand this, like the definition of f here.
It's just the expansion of your function. F is the function now. It varies in time. And I'm just expanding it in impulses of area what? It shouldn't be normalized. If I don't put this, then this is just a sum of impulses. right? But if I want to adjust to the height of the function, I need to multiply by the area of these rectangles. It's an approximation of the function by chunks.
Okay, so the impulse is f0. What do they look like?
No, h is the impulse.
Yeah, but it's a function of some f0.
F0, forget it. It's just the way you define your impulse. The impulse is ht. You can write it down here, but it doesn't matter. If you want, you can write it down like here. But it doesn't matter because now it will go away.
It's a Dirac function.
It could be a Dirac delta function. I mean, it tends to the Dirac delta function. Okay. Now, can we calculate the response to this f, which is now generic? L of f will be the operator gets inside the sum. Okay, these do not depend on time, so these are constant, right? They depend only on tau. And what do I get here? What's the response to the impulse? What's the letter I used? K, calculated where? T minus tau. Okay, this tends to an important formula that now we can try and understand. Okay? Everything is clear until here? So just to remind you, we are trying to understand whether that shape that I showed you there is interesting and useful, and I'm just telling you, please believe me, since chemotaxis is linear, it's gonna be interesting. And this is just a background on a linear transducer, what it does, and what's the impulse response in this context. Okay? Now we can use this and try and compute what are what is the response of a bacterium to a generic time course of attractant or repellent. Okay? And if you do that, you have to just compute that that linear response. So you could say, for example, that PR, in fact, what's linear in chemotaxis is the modification of this. So I'm gonna just already write it for, or actually no, I'm gonna write it for PR. Okay? What did I write here? The only difference in the notation is the fact that my, are there any other chalks? Yes. The only difference with that notation is that now my F is C, and it's the concentration of attractant. And where is it calculated? It's calculated on the trajectory of the bacterium. So the bacterium is running and tumbling and doing its own thing. So the amount of attractant that he gets in time depends on where he is in space. And that's the way you write it. This is the concentration that the bacterium gets at time t at the location where he is. Okay, a slightly more sloppy notation is C of t, which is identical to my F there. Sorry, of tau, of course. Okay? So let's get a pictorial view of this convolution. Okay, just for a second. I'll leave it there. What does that mean? Well, this is the time course, tau. Okay, and this is the concentration that the bacterium is experiencing in time. I'm integrating in d tau. Okay, so I need to see what's the concentration as a function of time tau. Let's say that the concentration increases. Okay, to calculate the response, so the fraction of cells that are running at time t, I have to do the integral of this c times what? Times k, which is this curve here. Okay, but calculated where? Is this right? Should I do the convolution with this? No. I should reflect this, right? Because it's in t minus tau. So this is now talking about the past. Okay, this is the response that you observe, and the way you use it in your model is talking about the past. Okay, it's modulating the response as a function of your past experience, which is nice because you cannot modulate responses as a function of the future. Okay, so this is not right. I'm going to just erase it because otherwise it becomes messy. Okay, this is the right one. This is k of t minus tau. So t is the origin, and then I have to reflect. Yes?
We have kind of like some kind of memory for
Yes.
but and eventually, like presumably, it goes like closer to its destination. It should be like more often than Tumble. But how does it store the memory?
How does it store? This is the most well-studied system ever. So I don't know the details, but so there is essentially in the way the kinases and phosphatases change the direction of the motor that controls the flagellum. So I'm not going to talk about it because there are details that I forget, that I always forget about it. But there's beautiful work about it, and you can actually monitor molecules so that everything is worked out for this system. So we know where memory is stored. Okay, but let me get to the punchline, because I think because everybody knew chemotaxis, everybody knows that that's gradient descent, right? That they are using the gradient, right? But did anybody know where it comes from? Can you see it from here? Nobody knew it, right? Everybody knows that there is this. Maybe somebody knows that there's this. Everybody knows that there's that. But this is where the fact that cells are measuring gradients come from. Okay? This is a linear system, and cells are responding as a function of what they got in the past 1 second, because that's the shape of this curve. Is there is a 1 second positive lobe and a 3 second negative lobe. Okay? So a flagellum will, a bacterium will respond to the difference between what he got in the past second and what he got in the previous 3 seconds. Okay, so you can approximate this convolution as C of past 1 second minus C of previous 3 seconds. Nice, no? And so this is the demonstration that if this is really a linear system, and if cells respond to impulses in this way, then they're responding to gradients. Gradients measured in time along their trajectory. Okay, and so I have half an hour, yes?
Yes.
So what I would like to do now is asking whether this is a good idea. Is it a good idea to measure gradients in time? Why not measuring in space? Okay, and this requires a little bit of basics in chemosensory principles at low Peclet numbers. Okay, what?
Play again.
Peclet, exactly. So we'll go back.
It's going to be the theme word.
it might be. So this is just a summary of what we just did. Oh yes, let's not go there because let's remain here at the title. Okay. Okay, so number one is I never know how to do this. Okay. Duck. Okay, let's do something very simple, which is the following. Okay, so you are a cell, and you are modeled as a perfect absorber. Okay? Around you, there are a concentration of molecules, so there's a lot of molecules, and they are transported by the advection diffusion equation. Okay, this is very similar to the Navier-Stokes equation. We'll talk about this because it's a great equation that shows very interesting, non-trivial properties, even if it's linear. It's linear in C. Okay, and you don't really need to do great perturbations to V to create something very interesting that we'll talk about tomorrow. Okay, so again, orders of magnitude. This is order U, C, let's say C infinity, so the concentration far away from the absorber, and then there is a length scale, and what is this? This is D, C infinity, and there is a length scale square. Okay, so what's the Piclet number? It's advection divided by diffusion, and it has a very similar phase to the Reynolds number. It has U, then I can cancel this, and it's UL over D, which is very similar to the Reynolds number, except instead of the viscosity, you get the diffusivity. Okay? And now, again, similar calculations. D are even smaller than viscosities in water. They're about 4 orders of magnitude smaller than viscosities. U and L are the same orders of magnitude we just calculated about, so this is definitely just a diffusion process. Okay? So at this point, this goes away. Okay, so you have a field, and let's assume that things are at equilibrium, and the chemical is such that the absorber doesn't modify it. There's nothing else in the universe. We are in the 3D space. There's a concentration at infinity, and then there is an absorber at this location. Okay, how many molecules impact the absorber? And now I want you to raise hands if you think that the number of molecules that hit the surface is proportional to the volume, to the surface, or to the radius. Volume, raise your hands. 1. Everybody has to vote. 1. Surface. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 29. 29. Radius. 7 maybe. 8 maybe. I'll say 8.5. I think it doesn't add up, so you know, somebody didn't vote. But I won't remember. I don't remember what I ate today, so it doesn't matter.
Especially the half doesn't.
It doesn't, yeah, I know. But that's fine. Anyways, okay, so let's do this little calculation because it's, in fact, it hides something very profound that I probably, we'll see if I have time. It's 10 to the 4 minus, 10 to the minus 4 of that, so it's about 10 to the minus 9. Let's see if it works. 10 to the minus, what was it, 5 meter per second, 10 to the minus 6, and then 10 to the minus 9. What? No.
No, because you have diffusion in the denominator.
Yeah, it's about 10 to the minus 9, I think. Is that right? It's only 10 to the minus 2? Is that possible? Maybe. Yeah. I mean, it's small anyways, but because the diffusivity for a chemical is typically this order of magnitude, which is smaller than viscosity. Okay, so I did it the other way around. But anyways, it's small. Okay. So we're here. So okay, so we have a chemical. It's diffusing to an absorber, and we want to know what's the diffusive flux. So do we know how it's defined? There's a minus. Everybody's sleeping. Right? Do people remember? Okay, this is the specific flux, and then we'll calculate it over the surface. Okay, and so we'll write this, since there's nothing else in the world and the absorber is spherical, we'll write it in polar coordinates, which gives this. Okay, so this goes away. So drc is, r squared drc is a constant, so the constant I call it a. I divide it by r squared, and then I integrate once more, and I get c equal minus a over r plus b. Okay, and I'm saying that at infinity, this is c infinity, and then I need another boundary condition, and because this is an absorber, I'm going to say this is 0. Turns out this is not, I mean, this is true, although bacteria are not perfect absorbers. But we'll talk about this in a second. Okay, so C of R, we'll call the radius of the absorber R, is equal minus A over R plus C infinity, and it's 0. That tells me that A is equal C infinity times R. Okay, and so finally I have that C is C infinity times 1 minus R over R. Okay, so now if I calculate the derivative, I get, what do I get? CR equals minus C infinity R divided R squared, and there is a plus here. Okay, and then if I calculate this in R, this is C infinity divided by R. Correct? Analogy with an electrostatic potential. This is all very good. So now we can calculate this, and actually let's just calculate the total flux. Okay, total flux to R, and we'll call it big J equal minus D times this, and since this only depends on R, it's a constant at R constant, and the minus sign is just because the flux is coming in. Okay, so that's right. Okay, so most of you, without doing the calculation, answer that they would expect the flux to be proportional to the surface, because that's very intuitive. You think bigger surface, more angles, more surface to hit, but this does not turn out to be true, and the reason why it's only proportional to R is pretty profound, I think, and I found it very interesting to derive. And I'm not sure if I should do that or tell you the punchline of this. I think I'm going to tell you first the punchline of this, and then we're going to move to that part if we have time. Okay, what's the punchline of this? Well, so remember, we observed the function. We decided that that's an interesting function because if it's a linear system, it tells me through a convolution that what's the response of the bacteria. We decided that that kind of function implies that bacteria respond to differences in the chemicals that they experience along the trajectory, and now we're asking, okay, I know about chemotaxis, I know they measure gradients, why do they measure them in time? Okay, and so this is why we started to blurb about diffusion and about how many molecules hit the surface of an absorber, because now we can calculate fluctuations. So what is the cell doing? The cell is counting. It's counting the number of molecules that are hitting the surface. Turns out it's not exactly what it's doing, but almost. Okay? So the n, so the probability to count k molecules if the flux is j and in time t is just given by, well, actually I don't even need to write it because I'm not going to even use it. Somebody knows how this is called. Okay. So if you count, you know that the average k will be just your rate of encounter times the time you measure. So this is equal to jt. And also another property of the Poissonian is that sigma square is also equal to jt. And so the relative error that you make in counting, so we'll call it sigma divided by k, is 1 divided by square root of jt. Okay? And now I want to do two little calculations. Was it a good idea to measure gradients in time? Well, if you want your gradient to emerge from the noise, you want whatever you count, which is what? It's dtc, it's the derivative of c in time, times the time of integration, divided by c, to be larger than delta c, or there we called it sigma divided by, you understand, this is proportional to delta c divided by c. Okay, so we have this. This is 1 divided square root of what? The time of integration times j, and j, we calculated it. It's dc infinity 4 pi r. And this, in order to get this, actually, let me write it down in the following form. T dxc times the radius of the cell divided by, no, it's not negative just because it comes in, but it doesn't matter. What I care about is the modulus. It's just coming in. Okay, so where was I? Yes. Okay, and I just write it in this way because I know from experiments that this number, epsilon, is order 10 to the minus 6. So these are measures. Measures that demonstrate that in a gradient coming from C about 10 to the minus 3 molar, which means 1 mole per cubic meter, which means 6 times 10 to the 23 molecules per cubic meter, they're able to do the job. Okay, so I have epsilon, I have C. What else do I need? That's all, I think. So there is T epsilon. I want this to be, so let's square it. There is an R. And here there must be something else, I think. What is there? Ah, yes. Sorry. Velocity. So I'm just saying the bacterium is moving and it's measuring things from here to here, and the time derivative is equal to the velocity times the spatial derivative. Okay, and so here I divide it by R, and this is the number that I know. That's the only reason why I multiply and divide by R. Okay, so TV, sorry, jet lag is kicking in. TV epsilon divided by R larger than 1 over square root of 4 pi R T D C infinity. Okay. So now if you work this out, you square this and you square this, and you have that T cubed, because this goes on the other way, is larger than R squared divided by R. So I only have R here, and then I keep 4 pi. R is gone, T is gone, D, C infinity, V square, epsilon square. So now the numbers, you have the numbers. C epsilon were the hard ones. D is typically 10 to the minus 9 square meters per second. V is 20 micron per second. And if you plug everything in, what you get is 0.7 seconds. So I didn't do anything very hard. It's just to say that the time that this device is measuring the gradient needs to be larger than 0.7 seconds in order to overcome errors that you incur to, even if you are a perfect absorber. Okay? And so what happens if you, instead of measuring in time, you measure your gradients in space directly? And so if that's the case, we can repeat the argument, but now here, this is not the signal anymore. The signal will be R dxc, right? If you measured differences across your body, okay, that would be R dxc. So R dxc divided by c. This is exactly this number that is always epsilon. And this should be larger than 1 over square root of T d C infinity 4 pi R. So now T goes the other way. We have to square again. We'll do epsilon square. And then we have T larger than, everything remains the same. You just exchange epsilon and T. And if you calculate this, it turns out the same numbers. So you can try and see if I misspelled something. This turns out to be 100 seconds. And 100 seconds is too long for a very simple reason, which is that bacteria don't keep straight for 100 seconds. Okay, so even if they wanted to, their signal would be completely washed out. They don't know what's their direction anymore. They cannot. So this is not possible. Bad idea. Okay, notice that if you had a much bigger R, that would be possible, in fact. And this is what some other organisms do. Even amoebas, I think, do measure gradients in space. There can be 100 microns in length, and that's enough. Okay. So I'm almost through, and I think I would like to at least sketch this thing that I just told you about, because there is very nice work about chemotaxis. So 2 things that I want to mention. One is that we didn't talk at all about the shape of this curve, of this response curve, and there is beautiful work about it, what shaped it. One particular thing that you might notice is that the area of the positive lobe is equal to the area of the negative lobe. Okay, and so what that means is that simply from our convolution, which might still be here, how does that work? Yes, from this relationship, if K has 0 area, what this tells us is that if C is a step, so if eventually you go through a step in a chemoattractant, but then that level remains constant, then the bacterium doesn't respond anymore. This is what's called adaptation, and it's a pure consequence of the fact that this positive lobe has the same area as the negative lobe. I didn't do anything about it, and I'm not going to mention it again, but there's beautiful work about it. So one thing I wanted to do in the last 5 minutes is to tell you a little bit more about this microscopic picture right here, because that informs something very important about chemotaxis, which is how a cell is supposed to put its absorbers, its receptors on the surface. Okay. Okay. So
amoebas, but amoebas are less low Reynolds than bacteria.
They are slightly higher Reynolds. That's right.
But
There's probably
do they
10.
ever get into like crossover regime?
So no, but yes. So one thing so there are very nice arguments about because as you move, so you could measure gradients in space, but as you move, there is just the fact that you're moving makes it that you receive a little bit more on the front side than on the back side. So that is bad for bacteria. Like I didn't even go into there, but because that argument is enough to kill the gradients in space. But so for bacteria, that's really bad. So I don't know if amoeba get out of that regime. They probably do, because I think they have responses that depend on the different activities back and forth, backward and forward. Okay, so a crash course on a microscopic interpretation of diffusion equation. Okay, I think everybody has seen it, maybe, but maybe not. So first of all, okay, so the goal first, just for that to be clear, so if you space out, you know where you are, is I want to tell you why the probability to capture a molecule that's diffusing toward an absorber is only proportional to R and not to its surface. And it turns out it depends on the fact that random walkers hang out a long time around surfaces. Okay? And the way to demonstrate that is, first of all, you can demonstrate that the laws of diffusion can be interpreted as a Fokker-Planck equation, so an equation for the probability that a random walker is in a certain position in space. Okay, this is a 2-line calculation, so I'm going to do it. Or did everybody see it already? Should I not do it? No. Or are you sleeping? No, not yet. Okay, because I am kind of, so. Okay, Jx, so what did I want to do? Okay, this is x, and this is x plus delta, and I have random walkers that can be on each of these discrete points in space, and I ask myself how many random walkers cross the surface from a time step tau to the next time step. I have discrete time steps, and they can either move left or right, one dimension. Okay, so J, the number of guys that goes to the right, is what? Well, half of the ones that were here will go left and half will go right. Same thing here. So then the number of them that go right will be 1/2 of, let's call that n of x at time t. Okay, that's the positive one. And then minus 1/2 n of x plus delta at time t. Okay, this is the numbers, but I want fluxes, so I have to do what? I have to divide by, okay, these are numbers, so I want concentrations. And then what I want, okay, concentration, so this is the volume, right? So now these become concentrations. And what I want to do is make this delta is the space. Delta. A is the area of the surface, whatever that is. So that N divided by A delta, this is the volume. So these are the concentrations. I'm still missing something. Okay, I want to divide also by delta. So I'll multiply by here, delta square. So this accounts for this delta. Okay, that's good. And then the area, that's it, because this was a flux. So it was a number crossing divided by the area. Okay, and then I multiply and divide by delta square. One delta remain here to make the volume and give me concentrations, and the other delta goes here. Okay, now I also have tau, so the flux times the area, that's how I should have done it. The flux times the area times my time step. So here I have a tau, okay, and I'll put it here, here. Okay, sorry, it was a little bit of a mess, but this gives you a microscopic interpretation of what's d. D is the square of the distance between the steps. Okay, so the step length square divided by the time step. Okay, microscopic interpretation of the diffusion constant in 2D. Okay, let's see if next one is slightly better. Okay, I have a volume and I just do volume conservation. Okay, so I want to understand how the J's, so again this is x plus delta. The J's entering and exiting a given volume change the number of walkers inside. Okay, so let's try and do this right. So J of x at times t times the area and the step, time step. This is the number of walkers that enter, must be equal to J of x plus the delta and tau and t, sorry, a tau. And then there is what? Sorry, let's do it this way. Sorry. So the number here is the number at the previous time, okay, plus whatever enters, which is what comes from x, and minus whatever exits, which is here. Okay, so same things. If you divide n by A and delta, that's the concentration, because this is the volume. A, again, is the cross-sectional areas. Delta is the width of this volume, so you get concentrations. Here you get fluxes, and let's not do the algebra because I'm too tired, but it works, I swear. And this gives us okay. So you put together this, and you get the diffusion equation. Yes?
Okay. What is your definition of concentration? Is it numbers?
Numbers divided by volume.
Yep. So in that step where you wrote the flux, right, you multiplied, in the very
Yes, because I need, so I should have done it like I did here. So J times T times A, this is numbers, you agree? And so these are numbers, and I don't have any constants here, right? So then I multiply by delta square, and I divide by delta square, and what I get is I take 1 delta to make the volume, that gives me the concentration. 1 delta to give the derivative, and that's good. And this delta square remains as the diffusivity. Okay. Okay. So this microscopic interpretation, so I'm not going to do the next calculation, but it's a 2-line calculation, and if you're interested, I can do it next time. This calculation shows you that if you want to know how many molecules move, so the diffusive, the concentration of a quantity that's diffusing towards the absorber is equal to the probability distribution that random walkers are in different positions in space. Concentrations are equal to probabilities. Okay, so this law here, the consequence of this, and again it's a 2-line demonstration that's really elegant, is that if you calculate how many times a random walker will hit the absorber before wandering off to infinity, that number can diverge. If you start close enough to the surface, that number can diverge. So that means that, for example, one important consequence is that bacteria don't have to cover their surface in receptors, because anyways the ligand will hang out there for a while. So it has multiple trials, and it will probably bump to another receptor even if it doesn't at the first bump. Okay, so that's one important consequence, and it's also the reason why the probability to absorb things doesn't depend on your surface but on your radius if you're a spherical absorber. There are mathematical interpretations with harmonic measures and stuff. This is really just a very deep result. I think I'm
Yep, you're out of time.
out.
All right.